So hopefully now that we're well versed in reference frames and Lorentz transformations and everything like that, we can now start putting it into practice and deriving some of the relativistic physical effects that special relativity is so famous for. So hopefully by now we should be familiar with the idea that space-time is a manifold, which as an object is something kind of raw, underlying, topological, and then to that manifold we assign quantitative or concrete number values by creating what's known as a reference frame, or just the coordinates that we use to describe the space-time. And those coordinates are intrinsically tied to us as an observer. We are tied to sit at the origin of our coordinates, and then the number values of our coordinates are just the number values we assign to the events in space-time. And so any two different observers might be assigning different number values to the events in space-time. So you could have some other observer y that, for example, sits at a different location in space-time, or we could even consider an observer that moves relative to this first observer, that travels along some world line. And we've seen how we can arrive at the reference frame of an observer that's travelling relative to us with some fixed velocity using our Lorentz transformation, which we've kind of started getting a geometric feel for what the Lorentz transformation or the boosted coordinates are going to start looking like. And so we now have all these different possible observers assigning all these different possible values to quantities in space-time. Are they all agreeing? Well, they're agreeing on the underlying physical property that this is a manifold. All of the points in the manifold have to be independent. They don't matter what coordinates you use to describe them. But now what we're going to see is that quantities observed in different reference frames aren't going to agree. So for example, the coordinate time interval between two events might be different in one frame to another, and we're going to see that this is now the origin of all of the physical effects like time dilation and length contraction that we're expecting to meet in special relativity. So I've already started briefly introducing this one of these notions, which is the notion of time dilation, because every observer is essentially dealing with their own time coordinate. That's not necessarily going to be the time coordinate measured by another observer, and so time intervals in one frame might appear differently in another frame. So we've introduced this notion of proper time, which is the time you experience in your own frame, i.e. a frame in which you're stationary at the origin, you're not moving within that frame. And so your world line in your own frame defines your proper time. And this proper time we understand as being the length of your world line in your own frame. And we saw we had quite a nice relation that the line element is always related to the interval of proper time that has elapsed. And we could use this fact to realise that now the line element, as it appears in any other frame, well, the value of the line element is always going to be constrained by the rest frame, i.e. the amount of proper time which elapses is a fixed quantity, it's fixed in the rest frame, and so all other frames have to then effectively distribute this proper time interval over now some space and time pieces. So I've already started introducing this idea and how we can start playing around with these intervals, but I'm just going to repeat it now here. If I just remind you that now the general line element for any reference frame is the following. And so just by the invariance of the line element, we know that these two quantities need to be equal to each other because the line element is invariant. So let me just rewrite. This is now the expression for our line element, or rather now the length of proper time which this observer has experienced in their own frame. But now if we want to translate this length into some other frame where the length might say not only lie along a time axis, but it might have some space-like dx and a time-like dt piece, we need to always make sure that the overall length, d tau, is constant. So as we shift these, or we distribute this length over these intervals, we're going to see that the values of these intervals are going to change in order to keep d tau constant. And so I played around with this a little bit more. Remember I showed you we were visualizing this using some kind of vector diagram where we draw positive additions to the line element in that direction, so that might be a dx. And then here we might have some dt, and then we're realizing that we need to add the dx, subtract the dt, so that the overall length of the line element d tau squared is always fixed. And then I played around with this a bit more and I found an even nicer way to visualize this, so I might not even bother showing you the previous one. But now what we can do essentially, we're trying to keep this d tau a fixed quantity, and then what I'm going to do is I'm going to allow this dx to vary slightly, increase slightly from 0, i.e. we're taking this completely time-like interval, we're shifting it slightly to allow for some small non-zero dx piece. But now quite a nice way that we can rearrange this expression is in the following way. If I simply just effectively add this to both sides and add that to both sides, I'm just swapping the two over, I'm going to arrive at the following expression. All I've done is just rearrange this expression, but now this expression is nicer, arguably nicer, for the argument which I'm trying to do, because this is now resembling a Euclidean addition of distances. So we can realise this is now effectively describing the following right-angled triangle. So this dt is going to be our hypotenuse, or rather c dt. Then we're going to have d tau squared and dx squared being our other sides of the triangle. So I'm going to say that this vertical side is our d tau interval of proper time, and then this horizontal is our dx interval. And so now if we understand this as a vector picture, choosing this point to be the origin, this is the vector d tau plus the vector dx, or rather I should be calling these the squared intervals. And we're simply just adding these two together to achieve the vector dt squared, and then just from this vector diagram you can rearrange and find that this d tau squared is going to be this vector minus that vector, with an extra overall minus sign, that doesn't matter. But what I want you to now see from this diagram is that now as we allow this dx squared, if, say initially we say that dx squared is going to be 0, i.e. our only vectors are going to be d tau and dt, they're both now just going to be pointing straight up with the same length. But now as we effectively pull our dt vector along, or we start adding in a small non-zero dx squared, we can see that in order to keep this right triangle consistent, I'm not very good at drawing straight lines, but to keep this right triangle a right triangle, this length d tau has to now increase slightly. Just now really carefully using Euclidean reasoning on this picture, because it is a Euclidean right triangle, this hypotenuse is longer than this length d tau squared. We just need to be really careful that we're using Euclidean lengths on a picture like this, because it is a Euclidean picture. but we need to remember that we're kind of being a bit sneaky and using this to represent this Minkowski line element. And so what we should kind of keep, or realise, is that we want to keep this, the tau squared side of the triangle, if you like, to be constant, and then we just allow this dx to increase slightly. And what we're going to see is that as dx squared increases from its value of 0, this dt squared is going to have to now start increasing, because quite clearly, if dx squared, well, if it started at 0, then we just have that dt is d tau, and then as soon as we start adding on some amount dx squared, from here, if we start adding on some larger dx squared, this dt is also going to have to increase if d tau is constant. And so hopefully a diagram like this is helpful to then help you visualize how increasing the dx squared is going to also have to increase the dt squared interval. And now how we should physically realize this is that what we're doing is we're taking our stationary observer's world line, which has a fixed length, and then we're looking at how that world line would appear as if we were watching this stationary observer moving, i.e. they're moving, so their velocity vector has some spatial component, and their infinitesimal length along their world line isn't going to be vertical. Their world line has some component in the x direction, and so as this x component increases, the coordinate time interval, dt, is also going to have to increase. And so the time interval is measured by the coordinate system. Remember, t is tied to the coordinate system of our other observer. The coordinate time that this other observer measures is going to be larger than the proper time measured by our observer. So this is sometimes stated as moving clocks run slow. If you're stationary and you see that clock moving, you're going to think it's effectively ticking faster than it actually is, because the time intervals are going to have to be greater in your stationary frame. So this is the physical phenomenon now of time dilation, that lengths, or rather the time interval as measured by an observer who is looking at a moving observer, the time interval as measured by the stationary observer, they're going to think that stationary observer has experienced more time than they actually have. So some famous paradox, like the twin paradox, where if you start with two observers at the origin, you let one of them be stationary, and you let one travel very fast in some direction and then come back again, well, this A is going to have to have experienced some length of proper time, d tau, but now the observer who went travelling off in space through the A reference frame, their d tau interval is no longer pointing straight up d tau, it has some spatial components, and so this A is going to measure the length of their world line to be now not longer, the overall world line has to have the same length, but just the distribution of those lengths in the space and time directions is going to be different than if the world line was just pointing straight up. And it's in these differences in the space and time intervals, as we're seeing here, that leads to the frame A thinking that this observer experienced a greater coordinate time than they actually did in their own reference frame. So this has been a very pictorial and kind of hand-wavy definition of time dilation. Hopefully it's quite a nice and easy visual way to see just simply how time intervals are going to change as we move into different reference frames. But now let's use our Lorentz transformation to arrive at some more concrete expressions for how we deal with this time dilation.